This is tutorial 4A of Laplace transform. We'll go through question 1 now. In question 1, remind ourselves this is the Laplace transform of f of t. We are supposed to integrate f of t with this expression to get f of s, the Laplace transform of f of t. You are integrating from minus infinity to infinity of t, the function f of t multiplied by exponential minus st. The question asks us what is s for part A and what is to interpret this equation. Let's start with s first. S is a complex number. So what is a complex number? It is this little guy here. On the blue line is the horizontal axis, which is the real line. Starts with 0, 1, 2, and so on. On the left, going left is -1, -2, and so on, going forever. The plane of complex number has the additional vertical line, which is the imaginary line. The origin is the same, j, 2j, 3j. Going bottom is -j, -2j, -3j. Any point on this plane is called a complex number. So we say the plane of complex number. S is a complex number. Whenever we can pick any number on this complex plane and we can put it in this value s. So typically s is a plus jb, the real part and the imaginary part. A is anywhere along this real part, b is anywhere along this part. So if I want to choose here, therefore this is 1 plus j1. And if I choose along here, it will be 0.5 plus j1. This is j1 here. Once I have fixed the value of s, I can substitute into e minus st. So we just put this is a again, and this is jb. So b is 2 pi f naught. Typically, b we can also write as omega, and omega it has a unit of radian per second for the continuous time part. We can then break this exponential into two parts, e minus sigma t multiplied by e minus j 2 pi f naught t. Let's plot this figure. This figure shows that as we increase time along here, I'm plotting discrete time, but it's the same, you interpret it well. And I have a positive omega. When I put a positive omega, the complex exponential will rotate clockwise. The reason is actually because there's a minus sign. So maybe I should just say it is a minus omega naught. When we have a minus omega naught, so we have minus, and this is omega naught, it will rotate clockwise. Along here is the real axis, and along here is the imaginary axis, and along here is the time. Let's see the next page. In the next page, I'm going to plot in discrete time 0.99 to the power of n times exponential of j omega n, and I'll select two omega. One is a positive omega, one is a negative omega. In the positive omega case, this complex exponential is rotating anticlockwise. When omega is negative, it is rotating clockwise. So here you can see the three-dimensional complex exponential. Here you see the two-dimensional complex exponential, and here you see the plotting of real versus the imaginary across different time. So how does the positive or the negative omega changes the rotation? You can study it from the real and imaginary part of these two diagrams. On the top is positive radian per sample. On the bottom is negative radian per sample. The key difference between these two is the sign, the imaginary part. The cosine is coming down because it's 0.99 to the power of n. Here, we are positive radian per sample. As time is increasing, we are producing the sinusoid, but it is becoming smaller and smaller. However, at negative radian per sample, as time is increasing, we are actually plotting the inverted sign. And because of this inverted sign, the value of the dotted points are coming down, because this is the imaginary number. He's coming down here, and therefore he's coming down here, and therefore this is a clockwise direction finally. You can play with the code here to see the simulation. Thank you.